important. Great. Thank you for the reminder. And now this is where we're left at, I believe, right? So we have talked about uh, for the shear design part. Let me zoom in so you can see better. Apparently it's a little bit vague. Um, there are two parts of the concrete that can take care of shear, right? So there's a concrete part, concrete component. Let me use red here. And there's a stirrups, right? The steel component. Excuse me. And from the applied shear force, that is factor shear force, right? So we can use the strength reduction factor. Strength reduction factor, mind you that this is 0.75 universal for shear, 0.75 universal for shear. Use that factor, we can find out the required shear capacity. Okay? So this required shear capacity subtract VC, which is the concrete contribution, right? And you can get the required contribution from the steel. All right, and we talk about that for the concrete. There are three main mechanisms, right? There's a Dowell reaction. This is Dowell reaction. I always call it reaction because it's research. Sorry, Dowell action, and this is aggregate interlock. Okay, and this is shear from the compressive zone, right? Shear from compressive zone. And if you're smart, you notice that I start writing, and that's probably going to be on the exam, right? It's probably going to be on the exam, right? So three mechanism constitutes the shear resistance from the concrete part, okay? And to estimate, right, we introduce an equation you can find from ACI 22.5.1.5.1, and that is the 2 lambda square root f prime c BWD. Now, don't confuse yourself. Here's a lambda, but this lambda is not the strength reduction factor. This is the concrete normal weight or lightweight factor. If it's normal weight, lambda equal to 1, lightweight 0.75. Okay, so that is the reduction for the concrete contribution. Okay, so F prime C is compressive strength, BW is the web width, and D, of course, is the depth of the beam. So you use this equation to estimate how much concrete can contribute in terms of shear, right? And let's take a look at the steel, right? So we talk about this. One big assumption we assume here is that the shear crack follow a 45-degree angle. 45-degree angle of a diagonal crack. 45-degree angle of a diagonal crack. All right, so that means the depth D equal to the width of the crack D here. All right, so these are equal to each other. Why is important? Because with that, we can estimate how many stirrups cross-cutting the width of the crack, right? So we can estimate the number of stirrups using this equation here, D divided by S. D divided by S, where S is the spacing between stirrups. Okay, so the name of the game is to find out how much area of reinforcement needed across this crack, right? So you use AV, which is the stirrup cross-section area, 2 legs usually, right? 2 legs, right? I draw here, usually 2 legs, right? So with this, we can actually estimate how much of a contribution each stirrups, right? You can think of this as single stirrup contribution. Okay, and then you can estimate how many bars or stirrups I need to give you the required steel contribution, from steel, right? So that is the equation, right? So if I have a stirrups that is inclined, and mind you that angle here is alpha, but you can also use this one, it's the same thing, right? They're identical. That's the inclination angle alpha. With that inclination alpha, you have the same equation as before, but with a factor that multiplied behind, which is sine alpha plus cosine alpha. All right. So with that, we have summarized the table here for you to do design. We have summarized a table here for you to do design. That is VC equal to 2 lambda squared F prime C, and it's in PSI again, and then BW, which is the width of the web, and D, which is the depth of the beam. All right, and then for the stirrups, depends on the situation. If it's a vertical, you use this blue boxed equation where we used often, right? We use this equation very often. And if it's inclined, just multiply a coefficient behind it. Just multiply a coefficient behind it, okay? But we don't use that inclination very often, okay? So most of the time you see the blue box equation, all right? So afterwards, you have Vn, which is the nominal shear resistance from concrete and steel, add them up, and then do a phi strength reduction factor, and remind you again, this is 0.75 in front of it, okay? To make sure that is bigger than the applied shear, okay? All right. So we left the quiz, right? We left the quiz here, and this is the box, right? We have a box, well, rectangular section and a box stirrups, number 5 stirrups, and we have the strengths, and we will ask you to find out the concrete, and we want you to find out the contribution from steel. All right. So this is where we left off from last time, right? Okay. So continue. Well, I believe you have done this exercise, right? But let's just continue for our next lecture that give you more of the insight on the design part. Give you more insight on the design part. Okay. All right. So last time we asked you to calculate the contribution from the concrete and from the stirrups, contribution from the concrete from stirrup, but we haven't asked you to do design. All right. So today we're going to talk about a design perspective of it. So lecture 13, design for shear part 2. Okay. If last time we have is part 1, this is part 2. Okay, now the objective is familiar with shear design process. Oh, sorry. Process for RC beam. How to design, right? How to design. Okay. All right. So let's take a look at some concept first. First of all, 13.1, right? There's a minimum shear reinforcement. Right? So just like we had for the flexure, there's a minimum flexure reinforcement. There's also a minimum shear reinforcement. Minimum shear reinforcement. So what it is, right? What it is, right? So this is basically saying even if your phi Vn equal to phi, well, let me remove this n, Vc plus Vs is greater or equal than Vu, right? This is the design equation, right? And even if, right, further, if phi Vc, okay, greater or equal than Vu, that is, if the concrete contribution itself is already bigger than the applied shear, right? Does it mean no stirrups? Meaning if my concrete can take care of the shear, right? So why should I need stirrups? Why should I need stirrups? Well, the answer is no. Okay, answer is no. We still need stirrups. Okay, because since shear failure is a brittle failure, right? Shear failure is a brittle failure. That meaning once it fails, there's no time to run. There's no time to run. So since shear is brittle failure. Now ACI dictates that. ACI, let me write down the section here, 9.3.3 dictates that requires a minimum reinforcement, shear reinforcement. That means even if your concrete section is big enough to take care of the shear, you still need some stirrups. You still need some stirrups. And this stirrup is called AV min. AV min. Okay. And this AV min equal to 0.75 square root of F prime C. Okay. BW, which is the width of the web multiplied S, spacing between stirrups, divided by the yield strength of the stirrups. Yield strength of the stirrups. And this minimum has to be bigger or equal than 50, okay, BW S divided by FYT. Okay, don't forget this. There are two lines. You take this value if it's bigger than the 50. If it's not, take the 50, right? Take the 50, right? So there are some exceptions where this minimum reinforcement does not apply, but very few. I don't want to distract you, but still want to put it here so you can take a look yourself. And you can find it in ACI 9.6, 9.6.3.1. Okay, and there's a table to tell you when and where this minimum reinforcement is different. 9.6.5, sorry, 9.6.3.1. Okay, in ACI code. in ACI code. So now, with all this, right? We have the tools. We have the tools to design for shear. We have the tools to design for shear, right? That is, now we know either way, we have to provide shear reinforcement. We have to provide shear reinforcement. So we have to design for it, right? Even if the concrete is sufficient. Okay, so this is how we're gonna go about. So flowchart, right? Process, right? So 13.2, design process. And of course, this design process is extremely simplified and for you right now. So we can take a quick look at it. So if we have a VU, that is applied shear, has to be smaller or equal than phi Vn, nominal shear resistant capacity, which is equal to phi Vc plus phi Vs. C represent concrete, S represent steel. So we know that from this equation, Vs, mainly for steel, has to be bigger than equal than Vu divided by phi minus Vc. Okay, so for the vertical stirrups, you see, automatically, we always assume vertical stirrups. The inclination, not so much, right? So Vs equal to Av, which is the shear reinforcement, Fyt, yield strength of the stirrups, D, depth of the beam, divided by S, spacing between stirrups. Spacing between stirrups. So with these two equations, you can solve. Okay, sorry. You can solve for the area, right? You can solve for the area, right? But typically we solve for spacing. So S required spacing, right? Spacing, stirrups spacing. We typically solve for spacing, okay? S required has to be smaller or equal than AV Fyt, okay? And D, which is the depth of the beam, divided by Vu, okay? Divided by phi minus Vc, okay? Vc, all right? So this is typically the equation we need, to design for stirrup spacing. So this is given stirrup size. Right, given stirrup size, design for spacing. Why so? Because typically for stirrups, we know that we either number 3 or number 5, right? Sorry, number 3 or number 5 usually. Okay. All right. So if you have the inclined stirrups, if you have the inclined stirrups, right? If stirrups inclined, which is very rare, but in case your stirrups inclined, again, let me say this again, do not design it to be inclined if there's no requirement, because they'll add on a lot of labor, right? Will add on a lot of labor. So that has to be smaller or equal than the whole thing, copy down, same thing as before, divided by VU minus V minus VC, right? But don't forget this whole thing multiplied by a factor, right? Sine alpha plus cosine alpha, where alpha is the inclination angle. So just to show you that this is the beam, this is the stirrups, and alpha angle is right here. Okay, so this is the required spacing. So let me just box it up so you know it, but we don't typically design for incline. We don't typically design for incline, okay? But still, you need to know, right? There are two types of equations, okay? So you see, it's not hard. It's not hard at all. It's not hard at all, right? And we would just go on and find out the spacing for the stirrups and calculate for it, and we're fine, right? But there are catches, right? There are catches, right? So now, if your VS comes negative, right? If VS is smaller than equal to 0, right? That means concrete is enough, or that is phi V C, actually half of it, okay? If half of it, half of the phi VC, all right? All right, it's, sorry, the other way. if VU is bigger than half of phi VC, but smaller than phi VC, okay? This is the requirement. Then, if this is the case, then we need a minimum reinforcement, that is AV mean. We wrote this before, equal to 0.75 square root of F prime C, okay, BWS divided by FYT. And this has to be bigger and equal than 50 BWS divided by FYT. Okay. So that is if the concrete is enough. The concrete is enough, but still VU has to be bigger than half of VC. Use this equation. Use this equation. Okay, minimum reinforcement. Okay, and in addition, there's another exception. In addition, right, we have to make sure at least one stirrup is provided in the shear cracking zone. Not very fond of this pen. Shear cracking zone. Okay, at least one stirrups that has to be fit in the shear cracking zone. What does it mean, right? What does it mean? Recall, I have a cross section, right? And we said we have a diagonal crack, like say, and I have a depth equal to the crack width, right? So depth equal to the crack width, right? To ensure I have one stirrups within this crack, right? That means I need to have at least one stirrups right here in the middle of it. That means if this is the spacing and that's the second stirrups here, and that's another stirrup here, if I need to have one stirrup sticking in the middle of the cracking here, I need to have a required spacing, half of the depth, half the depth. So this means, we use red. This means my required spacing after calculation, my required spacing has to be less than d divided by 2. D divided by 2. Okay, so means maximum spacing S max, okay, has to be lesser of 2, right? Half of the depth of the beam, or 24 inches. And this you can find from ACI 9.7.6.2.2. Okay. So although you have calculated the spacing from these equations, right? You have calculated your spacing from these equations. If it's vertical, you use the first one. Incline, use the latter one. But once you find the spacing, you have to go back and check to make sure that this maximum spacing requirement is satisfied. This maximum spacing requirement is satisfied. Okay. All right. Okay. So this is the design process. This is the design process. Okay. All right. Okay. But not, we are not good yet. There are also other constraints. There are also other constraints. Okay. So what are the other constraints? When VS, which is this requires steel reinforcement, right? When VS, right, is bigger than 4 times square root of F prime C BWD, okay, then S max is halved, reduced by half, right? 50%. And that's another requirement. So if you find out you have this scenario, then S spacing, right here, S max requirement becomes lesser of D over 4 half, right? And then 12 inches. And this you can find is ACI 9.7.6.2.2. Okay, so this is an additional requirement. All right, but you can see that the whole thing is very, very lengthy, very lengthy, right? There are so many requirements. So what you do? Right? So you have to calculate it. You have a minimum reinforcement. You have all this, and sometimes it's in terms of minimum reinforcement. Sometimes in terms of spacing. It's all over the place. It's all over the place, right? So let's organize them, right? Let's organize them. So to have what we call it a design table. Okay, so 13.3 design table for shear. Okay, it's more like a list. It's more like a list, but anyhow, let's see what we have, right? Let's see what we have. So this is the process. So first step, you check if VU, right? VU is smaller than phi VN, which means it's smaller than phi VC plus phi VS. We wrote this so many times now. Okay, so got this equation that VS has to be bigger than VU divided by phi minus VC. Okay, so you have to do this step first. All right, so after this step, we calculate the required spacing as required has to be smaller or equal than AV. Okay, AV, okay, this is two legs usually, right? Two legs of the stirrups, number 3, number 5, either way, right? Number 3 or number 5, either way, right? And FYT, yield strength of the stirrups, spacing between stirrups, sorry, depth of the beam, then VU divided by phi minus VC. Okay, so this is a second step that you calculate the required spacing. Calculate required spacing. Now the third step is to check maximum spacing requirement. So maximum spacing requirement. Okay, that is, I have to satisfy my requirement that maximum spacing, zoom in a little bit, has to be lesser or least of, okay, least of. I'm going to group all these requirements together, right? I'm going to group all these requirements together. Least of 4, okay? So you can think of it, this first one as D divided by 2, okay, or 24 inches. Now these come from ACI 9.7, 0.6, 0.2, 0.2, right? And also it has to be smaller than AVFYT divided by 0.75 square root of F prime CBW, or a VFYT divided by a 50 BW. And these are the minimum reinforcement requirement, remember? So just say AV min, okay? And this is from ACI 9.6, 0.3, 0.3. So we converted the minimum steel reinforcement requirement in terms of spacing. In terms of spacing. Okay, in terms of spacing. So the top is to ensure one stirrups at least in D, right? In crack with D. Okay, the second is the minimum reinforcement. So I just grouped them together. I grouped together. So once you went through this, and you have to check again to see if VS, that is the required steel, is bigger than 4 times square root of F prime C BWD, okay, then S max is halved, so it has to be reduced. So I have, let me just clear it from here, reduce here, okay, number 4 step, okay, so has to be halved, right? So now the required spacing becomes S max has to be lesser of 2, which are D divided by 4, or 12 inches. So this is again ACI in a code of 9.7, 0.6, 0.2, 0.2. Okay. All right. So just to clarify, right? Just to clarify. So this is a side note. Side note. Essentially, what you're doing is you can group all the required spacing. You can group all the required spacing, right? So this is basically done, right? That is all the requirement. That is all the requirement on the 4, number 4. Well, I will continue, but anyway, side note is, so far, essentially what you're doing is S has to be smaller or equal than the least, what happened to me today? Least of all these, right? All these, right? What are all these, right? So first has to be least of as required. Remember, calculated. That is AVFYT. Let me make sure I got it right. D S. Oh, sorry. No. I think I got it wrong. Let me just copy it down here. Yes. VU divided by phi minus VC. Okay, so this is the equation, right? Calculate equation, or D divided by 2. D divided by 2, or 24 inches, or AVFYT divided by 0.75 square root of f prime c bw, or a v f y t divided by 50 bw. Okay, now this whole thing, this box right here, okay, let me just draw it. This box right here is when Vs shear from steel is smaller or equal than 4 times square root f prime c bwd. Okay, this box right here, okay, is that, right? So let me just move this box a little bit on the left so I have more room here. All right. All right. Okay, good deal. Okay. So this is the one condition, right? And if not, right, or else, let me write out all these boxes right here. So your spacing requirement becomes as has to be less or equal than least of, right? So the required calculation still sits here, A V F Y T D depth divided by VU divided by phi minus VC, and bottom here D divided by 4, right? Halved, right? And 12 inches. 12 inches. Okay, and then all these, right? A V F Y T, you copied it down, divided by 0.75 square root f prime c bw, or A V F Y T divided by 50 bw. Okay, so this case, right? This case right here is for different scenario for when Vs is bigger than 4 times of square root f prime c bwd. Okay, so that's the second box right here. Okay, so this side note here is to summarize, essentially summarizing step 1 to step 4. Summarizing step 1 to step 4. Okay, summarizing step 1 to step 4. Okay, now one more thing. So step 5, if all these are satisfied, right? Pretty happy and we should be fine. But just don't forget, right? There are other miscellaneous small things you have to pay attention to. That is for stirrups, FYT, the yield strength has to be smaller or equal than 60 KSI. Cannot exceed. So you say, what if exceed, right? Right? So if say YT, for example, e.g. FYT equal to 75 KSI, you say, wow, that is bigger, right? So use 60 KSI instead. Okay, so the stirrups does not go above 60 KSI, and that is in ACI 20. Okay, ACI 20.2.2.4. ACI 20.2.2.4. Okay, so don't forget. Oh, my Siri is going crazy. But anyway, okay, so this is the, let me just cross it out. How do I do that? Yeah, sure, I know you're here. I don't need you right now, okay? So this is the stirrups. Okay, now, once we have done this, right, everything should be good and pretty, right? Except one thing, that, okay, 6, except one thing, right? If we still provided Vs max, okay, has to be smaller and equal than 8 times square root f prime c bwd. Okay, has to be bigger than that. Okay, Why is that? Because, and this is an ACI, if this violates ACI 22.5.1.2, if not, change section, BW and D, change section basically. Okay. So it says the provided steel cannot exceed 8 times square root f prime c BWD. If it does, then your section is just too small. If it does, your section is just too small. All right. All right. So this is the design flow chart. Design flow chart for shear. All right. So let's recap. So first, find out apply shear force. Okay. First step, right? Find out your shear, apply shear force, and find out how much stirrups you needed, VS, right? Calculate it and check your max spacing, right? If it's smaller than 4 times square root f prime c or bigger than 4 times square root f prime c, and you have different list of spacing requirements. If good, fine, move forward. Make sure the stirrups, that FYT has to be on the left side of 60 KSI. If it exceeds that value, use 60 KSI capped, and at the end, check the section, if the section is big enough or not, right? If the section is big enough or not. Okay. All right. So this is essentially all the equation you needed. Okay, for shear, all the equation you needed for shear. All right. It's a little bit dry still. I understand. Sorry for it, but this is what we have, right? A design flow process. Okay. And we will talk about how we're going to implement it in the next lecture. Well, actually on Thursday. On Thursday, we'll talk about how we implement it. All right. So we'll give you several critical sections first, of course, then give you a geometry and some bars. We can go design about it. Okay. But before now and then, I want you to review the shear design process just to get familiarized it. Okay. Just get familiarized it. All right. Any questions, folks? Any questions, folks? Are we good? Any problem with this? Okay. All right. It's pretty dry, I understand. And it's just the philosophy we had to go through for the shear design. And now Thursday, we start talking about examples and things will become more clear to you. Okay. And let me say this again in case you forgot. The homework number 6 deadline will be extended to next Monday. I will send an email shortly to let you know that. And we'll go over some of the tips on Wednesday, which is day after tomorrow, and also go over some of the problem from the exams. Okay. So if you have any more questions, welcome to stay behind. If you have any concerns about the exam, you want to talk to me, you're welcome to stay behind as well. Okay. If not, I'll see you on Wednesday. All right. Thanks a lot. Bye now.